Krzyzka is assistant professor at the Engineering and Technology Institute of the University of Groningen in Netherlands. Now he's leading a MetaMechanics group. The research field of the group is advanced materials and with the applications in acoustics, medicines, soft robotics, and many other fields. And Dr. Krzyzka published more than 45 papers in leading international journals, including Advanced Materials, Physical Review Letters, Journal of Mechanics and Physics of Solids, New Journal of Physics, Scientific Reports, and so on, and has 2 patents. She received several individual fellowships and Young Researchers Awards, serves as an associate editor and guest editors in more than 7 journals. She's now a reviewer for more than 50 journals and 3 international conferences. Is now a committee member and a remote evaluator for national and international funding agencies, including European Commission, Deutsche Funding Agency, Swiss National Science Foundation, and the French National Research Agency. The talk of his the title of his talk today is the metamechanics and patterned flexible wings. So please, begin with your lecture.
Thank you very much, Professor Wang. So first of all, I would like to say that it's an honor for me to be invited. So thank you very much, Professor Yan-Ten Wang and Yu-Shen Wang. Sorry if I pronounce it incorrectly. I'm really pleased to be here after such many great names who presented the previous 18 lectures before me. And thank you very much for your kind introduction. You saved my time. So instead of planned 55 minutes, probably I will talk for 50 minutes, and then we will have about 25 minutes Q&A session, if it's okay for you. Please do not interrupt my lecture with the questions. So if you have questions, note them down or put them in the chat or simply ask them after this lecture. So as Professor Wang said, the title of this lecture is Metamechanics and Pattern Flexible Wings. And first of all, I still have slides to introduce myself. My interests are in the field of wave dynamics, vibrations, acoustics, advanced materials, and a little bit in piezoelectricity, with the focus on architecture or advanced materials, which are better known to most of you as metamaterials and phononics. And as was said before, I'm an assistant professor at the University of Groningen since May 2019. Before I got my PhD degree and master's degree in Ukraine, then I moved to Europe, did a couple of postdocs in the Netherlands, in Italy, was a visiting researcher in France, and then returned back to the Netherlands. So this is in short. And to give you an idea where it is physically on the map, so Netherlands is in the north of Europe with the capital of Amsterdam, and Groningen is in the north of the Netherlands. So here this small dot. Groningen is has one of the 4 classic universities in the Netherlands. It's pretty old university. It exists since 1614, and this is the oldest main building. There all the PhD defenses take place, and it's located in the city center. Outside the city center, we have the Zernike campus with modern buildings and all the facilities for studies and teaching. And in this small building here in the left bottom corner, so this is the place where I'm located, and this is the place where we have a living Nobel laureate. His name is Ben Feringa. He got his Nobel Prize in organic chemistry in 2016, and now he's still an active researcher, having a large group, and we are sitting actually in the same building. Okay, so after this short introduction, I will present you also in short the activities of my group here at the University of Groningen, and then we come to the main topic of today's lectures. These are design strategies for patterned artificial winds, and at the end I will summarize with the lecture with some conclusions. So metamechanics, this is the name of my group, which currently has several PhD students, visiting students, and master students. And we position ourselves as a materials and mechanics research lab, which investigates fundamental relations between materials and their architecture, and also develops metamaterials for various applications. And now I give you several examples along these two research directions. So the first direction is about fundamental relations between materials and architecture. And the representative example on this is a recently published work on dissipative dynamics of polymer phononic materials that appeared last year in Advanced Functional Materials. And in this work, we analyzed the effects of viscoelastic material behavior, which are typically ignored. So this is not the common elasticity, then we have the glass transition temperature, but the so-called secondary relaxation zones. And how the secondary relaxation zones, being very small and resulted in small variations of elastic moduli, how they can influence the dynamics of phononic structures. So for that, we prepared some samples of phononic plates with band gaps at different frequency ranges, and showed that secondary material relaxation in polymers can introduce large changes in the wave attenuation of phononic plates, depending on the relation between the material properties and the frequency band gaps, and also the mechanism of these band gaps. So it's quite a broad topic. The paper is pretty large. If you're interested in it, I suggest you better to read the paper rather than I go to all the details now. Along the similar settings, we work also on the analysis of wave dissipation in 3D printed polymeric phononic structures. On this topic, we worked together with the Philips company. This company produced for us 3D printed samples, which we analyzed starting from the microstructural level, so performed the analysis of microstructure by using scanning electronic microscope, then also analyzed different material characteristics, and then by introducing different wave manipulation mechanisms, which are pretty known to the audience, I guess. So these are phononic band gaps, locally resonant band gaps, inertial amplification band gaps. We studied how the viscoelasticity of 3D printed polymers influences the wave attenuation and wave guiding properties in these materials. Okay, after these two examples, we go to the applications, and applications in my group are currently analyzed not in the phononics field, but in the field of mechanical metamaterials. So here you see an example of the work of current PhD student Jiaoheng Zhang. He works on automated design of programmable mechanical metamaterials. And in his recently published work in APL materials, he developed a new mechanical metamaterial configuration. So here you see an example of a metamaterial structure, which can be tuned by changing two parameters. This is the shape of this curve and the thickness of the elements to perform a shape morphing functionality. So basically the structure can imitate the shape of an object, and at the same time preserves more or less uniform stress distribution within the structure. That is very beneficial, for example, for energy absorbing properties. Another application, it's in the field of medicine, and this is the student, PhD student Jornitz Heinz, who will actually start on Thursday this week. But he already worked during his master project on the development of metamaterial implants. And for this project, we worked together with the university. There they treat cancer patients, and specifically we focus on cancer in and tumor in head and neck cancer patients. So in this example, you see a tumor in the mandible. And often for these patients, part of the bone should be deleted and replaced by an artificial implant. These implants are metallic, and metals have mechanical properties which are quite different from those of bones, as we know. That's why Jornitz works on proposing how to use metamaterial principles to change the mechanical behavior of implants to obtain the desired properties as close to the bones as possible. Okay, so to work on this and other projects, we also have MetaMechanics lab. So here is short video with the setups that we have. And specifically, we have facilities for additive manufacturing. And this is an FDM dual nozzle printer, SLA printer. We also have a laser engraving machine. And to test the manufacture samples, we have acoustic impedance tube and laser Doppler vibrometer with related other setups like amplifiers, transducers, accelerometers to perform ultrasonic tests. To have an idea of the tests that we do, please go to our website, and we also have a YouTube channel that has the same name, MetaMechanics. There you can watch videos on possible applications and the tests that we do in this lab. Okay, so after this short introduction, I go to the main topic. These are patterned flexible wings. It's a short title, let's say, and a longer title can sound like aerodynamics and aeroacoustics of flexible artificial wings with metamaterial patterns. So this topic is not pure on mechanical metamaterials, and it's also not pure on phononic metamaterials because I would say it's on the border. So that's application of mechanical metamaterials to the dynamics of flight. And we think that we are one of the first people who decided to study this field, and which is quite challenging and requires very different expertise that my group has. So that's why it was a highly collaborative research. And the initial idea of this research came from my Turkish colleagues. So this is Professor Mustafa Ranjbar, and he is at that time PhD student Mahmoud Yilmaz. They proposed this idea and developed the initial model, and to understand whether it's a good idea or not, we performed some experiments together with my colleague, Professor Ajay Katapali from my institute, and my former PhD student, Nitesh Anirao. After learning that the concept works, we decided to do more in-depth numerical studies and more serious analysis. And for that, we collaborated with Igor, who is from Swiss University of Applied Sciences in Switzerland, and also Dmitry Krushinsky on using the concept of machine learning for better predictions. So, and now I will talk to you what is all this about. So then you hear man-made wings. The first that you imagine is something like that, right? So these are the wings of airplanes. And if you imagine how an airplane flies, you immediately understand that the wings behave as rigid and they're fixed. Of course, they're not totally rigid. There is nothing absolutely rigid around us. So they still may exhibit some deformations, but these deformations are considered to be more undesirable rather than beneficial for flight. So that's why we can say that man-made wings, they're rigid enough for most common applications. However, if we have a look at natural wings, for example, at the wings of insects, they're quite different. So first of all, they're not fully fixed. They can fold, they can rotate, they can flap. Second, they're not rigid. They're inherently flexible. And apart from being flexible, they also have a complex structure. Just have a look at these examples, and you see that for every insect, the wings are patterned. So there are rigid wings that are arranged in so-called optimized patterns that provide some benefits to insects, and we will discuss these benefits later. And apart from that, wings are not only used for flight, but they're also used for communication purposes. So, for example, by flapping their wings, insects can communicate to each other about the presence of an enemy, or they can send the signal from female to male species. So it's inherently complex and multifunctional structures. And researchers have been interested in analyzing the dynamics of natural flyers like insects for quite a long time. And then they studied the advantages of flexible wings as compared to rigid wings. They found that having flexible wings is actually really beneficial. Why? Because it helps to save total power for insects. Second, it enables the insects to have high lift to height ratio, weight ratio. So that means that they can carry some weight in addition to their own. They also help to introduce better control of aerodynamic characteristics during the flight, and they allow them to be a little bit more tolerant to the wind as compared to rigid counterparts. So having all these advantages in mind, researchers have started to develop flying devices with flexible wings for quite a long time ago. And this research continues now. And here I show you my favorite example. This is a small flying device, which is inspired by dragon flight wings and the dynamics of the dragon flight. So fully artificial, fully mechanical. And you can see now, then it slows down how complex are the motions of these wings. Yeah, so they really experience large deformations during these flaps. Besides, you see that even this in artificial setting, and not speaking about natural, all the wings are patterned. And it appeared after many studies that this venation pattern is crucial for flight. Let's have a look at the model of a wing of a dragonfly. So this in brown, you see the venation patterns. Let's discuss it a little bit. So first, you can see this, the thickest vein, which is called the leading edge, which introduces, in terms of mechanical properties, anisotropy in the two directions. So this longer direction of the wing appears to be more reinforced as compared to the perpendicular direction. Then smaller veins introduced so-called local flexible regions. So they make the structure of the wing as reinforced in certain places and which is remained flexible in other places. So flexible is in green here. And after many studies, it appears that this variation in the patterns enables to control bending and torsional modes during the flight. And it's unique for every insect and also for every specific insect. So it's quite complex structure. Besides, we see that the veins have varying width. So they are thicker close to the base and they're thinner closer to the tip. That introduces the variation in the stiffness and the inertial resistance of the wing, which is also beneficial for flight conditions. But overall, you see that the structure of this pattern is not simple, not only from topological point of view, but also in terms of geometric properties. So if we want to describe it, we will really need a lot of geometric values to fully reproduce it. And this is one of the major challenges in modeling the dynamics of these wings and reproducing it in artificial wings. So what are these challenges specifically? So first of all, you see here some examples, and these are artificial wings, and more or less early works which rely on full finite element modeling of the wind dynamics, but still the pattern which is present is maybe even completely absent, just a leading edge, or present in a very simple form. And the reason is that the modeling is really computationally challenging. So that's why, to obtain at least first insights into the dynamics of the winds, researchers try to avoid having patterns. Then, as I already said, the complexity of the pattern and also the difference in the materials for natural winds and for artificial winds does not allow to directly translate the pattern as it is, because it's really the relation between the material properties and the structure of the pattern. At the same time, looking at the insects, we cannot find an, let's say, ideal pattern, because the variability of patterns is so great that it's difficult to understand which ones perform the best, if they can, it's possible in general to find the best pattern. The next challenge of working with artificial patterned winds is the absence or scarcity of suitable materials and technologies. And by this, I mean that you can see here that most artificial winds which try to mimic natural winds, they are made of very light and very fragile airfoils. And there is no unique technology to make them. So in most of the cases, these are manual designs, which requires quite a lot of time to assemble winds, and the fragile material results that they are, can be broken very easily. And also, the very thin material used to produce winds reduces load-bearing capability. That results in a lot of studies to optimize the flying body. So, looking at these challenges, we decided to address some of them and to have a look whether we can use metamaterials to obtain something better. So these are the challenges, and our goals were, so first, not to compromise in computational complexity. We decided to perform full-scale 3D fluid structure and interaction modeling to model the dynamics of these winds, because only in this setting we can get really useful insights into this, into the dynamics of winds. Then we decided to make a step away from the variability of natural patterns, and instead we use metamaterial type pattern. The idea here is that metamaterials have typically a few geometric parameters that allow us to obtain a wide range of mechanical behavior. But having a few parameters allows us to study how the design of the pattern can influence the wind dynamics by preserving the design space sufficiently small. So this was the motivation. To find suitable materials, we decided to explore 3D printed polymeric materials, because 3D printing becomes more and more affordable. We can print from flexible materials. It's not expensive and quite easy to do. So if we can make 3D printed polymer winds quite easily, then this may open a nice perspective for improving the design of artificial winds. And finally, to address the limited load-bearing capability, we wanted to explore the resonance flight conditions. Why resonance? Because at resonance, all the characteristics are amplified, and this includes flight. And there are actually natural insects which fly at a large distance, benefiting from resonance effects. So if it exists in nature, why not to exploit this approach for artificial winds? So with these goals in mind, I will introduce you the model that we created, how we tested it, and how we performed the modeling. And we start from the model. So our wind model is inspired by that of a dragonfly wing. And specifically, we took the overall shape, so we preserved the shape, and we preserved the external wane of its analogous. And to keep controllable area of the metamaterial pattern, we preserve the external wing from all the sides. So basically, we cover with the metamaterial only interior of the wing. For metamaterial pattern, we choose a very well studied, very well known honeycomb design. First, because it's simple. Second, because it allows to achieve a wide range of mechanical responses. And you can see here two important things. So first, our wing is not flat. So it's cambered or convex. And this is on purpose. So first of all, this is because natural wing is not flat. Second, because having non-flat wings provides some modeling, some benefits in terms of modeling. I will explain you this later. And second, you can see that we have the metamaterial pattern only on the top surface of the wing, not below. This is for simplicity. So in this model, we end up having 5 design parameters. This is the pattern area for the wing pattern. So this is P. Then out of plane and in plane stiffness of the elements. And also to have a little bit more design freedom, we introduced the so-called scaling parameters along the horizontal and along the X and Y axis in these terms to be able to make this pattern anisotropic. Okay. Then we decided to check if it is possible to produce these wings. And for that, we used dual nozzle 3D printer and flexible TPU material made from recycled polymers. And we ended up with having it printed. So you see in the variation of colors here that in certain parts, the wing is very thin. So it contains just, to be more precise, 2 printed layers of material. And this ensures the wing flexibility. To give you an idea how this flexibility works, and because we are not in a real audience but online, I give you here some demonstration. So we printed several samples which have different out-of-plane thickness. So for the first sample, we have 2 printed layers, for the next 4 printed layers, and so on, and for the last 10 layers. And this number of layers is used in the design of the wing. And then we fix one end of this sample, and the other will be loaded with a static mass. So this is not to test anything, but just to show you how flexible or rigid the material can be. So then we have 2 printed layers. You see that material is very flexible, and at the same time, it exhibits fully reversible deformations. So then we remove the mass, it returns to its initial position and shape. But if the number of printed layers increases gradually, you see that material behaves more and more rigidly. So this allows us to make a wing model made of from one material, so this TPU or recycled polymer, but at the same time control the rigidity and flexibility of material by changing the number of printed layers. And this is something that we also have in nature, because natural wings, they are made from a single material, it's chitin, and this chitin is differently arranged in the veins and in the flexible parts. So we were very happy that man-made material can have the same or analogous mechanical properties. Okay, so having printed these wings, we wanted to understand how accurately we can model them. And this is essential because, as I said, we use low-cost 3D printer, so the printing quality is not very good. And it's important to know how much inaccuracies are introduced due to the manufacturing process. And for that, we tested the dynamic characteristics of the wing. So specifically, we fixed the base of the wing in a holder and excited it from one side manually by a hammer. And at the other side, by using the laser Doppler vibrometer, we measure the free-form vibrations. So basically, we hit the wing and then let it vibrate and then measure the vibration response. So for the 3 samples that you see here, we measured many times the free vibration response. So here is an example of one set of measurements. And as you can see, the amplitude is different because we use manual excitation. So this is experimental data. We used them as initial input for Fourier transformation. And in the frequency domain, we were very happy to see that the first eigenfrequency of 3 different samples printed under different conditions, so under different orientation, is the same. And most importantly, it coincides with our finite element simulations almost perfectly, so the difference is negligible. And the agreement for the third mode is also quite good. So we were very happy with that, and then decided to check the next property. Are our winds robust enough to survive resonant type excitation? So for that, we use the forced excitation test. I will not run this video, you cannot see it much, but I noticed that then I ran it, my presentation is broken. So the PowerPoint does not work good with this video, sorry for that. But the idea is the same. So now instead of manual excitation, we used a shaker, excited it for different, excited the wind for different periods of time and measured the forced excitation response. So it looked like that. So we excited it for 5 minutes, then the next round for 30 minutes, and then the same wind for the next time for 90 minutes. And then after each of these forced excitation experiment, we performed free excitation experiment to check the eigenfrequency. The idea was that if there is a damage within the wind, then the eigenfrequency will change its value. But as you can see, after even 90 minutes excitation, the eigenfrequency value is preserved. That means that there are no essential internal or external damages in the wind, and in total, the excitation time exceeded 2 hours. That means that the lifetime of 3D printed wind is comparable to that which is typically used for microflying devices. So we can use these 3D printed winds in resonant type conditions and do not expect to have any damage because of that. Okay, being excited by these results, we wanted to model the wind dynamics. And for that, we chose for flap and flight because it's much easier to model. For that, we put our wind model in the half ellipse, which represents air, fixed the base, and applied a sinus loading at the bottom part of the wing, the bottom surface. And in this way, we can reproduce these dynamics, as you can see this animation on the right-hand side. We also assume zero angle of attack. Zero angle of attack, this is the inclination angle of the wind to the horizontal surface. And as I mentioned previously, our wind is cambered. That means that it will generate lift even despite zero angle of attack. That's why we wanted to have it cambered, to reduce the number of parameters in the model. Then we also did not model forward motion, did not model the influence of external forces, and also ignored the possible interactions of the winds with other parts of the flying device. These interactions might be essential, but as I said, our goal was to understand how the pattern of the wind influences its dynamic, but not to build the flying device. So that's why the assumptions used in this modeling, they are aimed to minimize the number of parameters so that we can in fully explore how different patterns influence the wind dynamics. So, and with these assumptions, we performed transient three-dimensional air-wind interaction study by using finite elements. The problem for air is described by viscous incompressible Navier-Stokes equations. So here they are. And we assumed laminar flow because the flapping frequency was low and small Reynolds numbers. For wind, we used equations of motions for the compressible elastic matter under large deformations. And these two domains were coupled together by using arbitrary Lagrangian Euleran approach. I'm not going to deep into details here. You can have a look at the paper if you're interested in how it was implemented. And by means of this model, we were able to reproduce the flapping motion of the wind. So here you see the in colors the variations of stresses in the wind material, and this blue strings show the velocity field in the air domain. Okay, so the model works. And to analyze the influence of pattern, we need to have some characteristics which we are going to explore. And for that, we introduced the lift force, so-called. This is the averaged volume averaged pressure at the top and bottom surfaces of the wind. And we introduced the average sound generated by wind and the defined the maximum stress in the wind material. And for these three characteristics, we want to have maximum lift force and minimum sound and minimum stress. These are contradictory requirements, and now I explain you why. So I do this by using rather complex looking maps, but I explain you how they work. So first, let's have a look at the top left map. This shows the dependence, the variation of two parameters along the horizontal and vertical axis. And the values uploaded in the map show the difference between the excitation frequency and the eigenfrequency of the wind. So what we do, we can change the values of these parameters, pattern parameters, and tune the eigenfrequency of the wind. And the colors show us how close we are to the excitation frequency. So specifically, yellow color shows that we are about 5 Hertz away from the excitation frequency, while dark blue color says that we are very close to the excitation frequency. Yes. So, and you see this dark blue region here, yeah, that corresponds to the parameter values. Then then the eigenfrequency of the wind approaches the excitation frequency. Yeah. And for this, in the same way, we construct the maps for our key characteristics. So for lift, for noise, and for stress, for the same parameters. And you can see that as soon as we are close to the eigenfrequency is close to the excitation frequency, the lift has maximum values. So here we should have a look at the magnitudes, not the sign. So these are maximum values. And at the same time, we have maximum values of generated sound and maximum stresses. That means the closer we go to the resonance, the higher the lift, but the higher are the other characteristics. And now we want the opposite. We want to maximize lift and minimize noise and minimize stress. So that's why we have a contradiction here. To solve it, we developed a multi-parameter optimization scheme, which can be separated into 2 steps. So first, we change the parameters of the pattern to satisfy our frequency objective. And frequency objective means that we want to tune the parameters of the pattern to have the eigenfrequency of wind as close as possible to the excitation frequency. And here you see the corresponding expression. So for that, we solved about 1,000 problems and constructed the frequency objective map, which shows us that in the yellow region, we are at least 1 Hertz away from the excitation frequency. While in the dark blue region, we are very close, so smaller than 0.1 Hertz difference to the excitation frequency, so really resonance type conditions. And for these conditions, let's have a look how closeness or staying away from the resonance influence the flight dynamics. So if you have a look at the real vibrations of the wind, you do not see much. So this is here on the right-hand side, but on the left-hand side, we can learn something from here. So this is the evolution of motion of a tip in terms of time. So first you see that vibrations are stabilized quite quickly. So after about 0.2 seconds, the vibrations become periodic, but to be sure, we analyze the time period starting from 0.3. And then the vibrations are fully periodic. And this periodicity is preserved in both cases, so whether we are far or close to the resonance. The difference is amplitude is not very large, but what we see for the resonant type condition is that there appears additional peak in the pressure distribution, which is also observed for natural insects which fly close to the resonant conditions. So we can reproduce this additional peak, and we were quite happy with that. So now, after having solved the first multi-parameter optimization step, we want really to tune the design parameters to maximize our lift and to minimize sound and stresses. For that, we use the results of the first step and focus on this small region, which is highlighted in dashed green, for which we are already close in terms of frequency to the resonance. Yes, this means that being in this region, we fix two parameters. This is thickness and pattern area, and change other three parameters of the pattern to achieve our goals. And within this small region, we can obtain quite different designs. So here you can see an example of 10 possible patterns, 2 of which actually satisfy the condition. So they indeed show that the lift is maximized as compared to a reference, and sound has minimum value. These are different designs, but at the same time, they exhibit some similarities. So you can see that the honeycomb is extended along the horizontal direction, so it's quite anisotropic design rather than isotropic, and this anisotropy is beneficial for our target characteristics. So that means that the procedure works, and we can apply it to use to develop some optimized design. So maybe not optimized in the sense, but at least to have controllable flight characteristics. At the same time, we were not very happy with that because you see that we initially chose some parameters like thickness and pattern area for the first step, but maybe these are not the best parameters. Maybe if we choose other parameters, the design, then we could obtain better results. So that's why there is really a need to develop a procedure which will allow us to explore the design space in full. And we did it as a next step. So having 5 parameters to describe the wind pattern, we have 5-dimensional design space. To explore it, we use the machine learning techniques. So first, we extended the design to include auxetic structures too, thinking that maybe auxetic material behavior will be beneficial for flight. And also, as you can see, it's anisotropic, and we saw that some optimized designs have anisotropy along the y direction. And with this extended space, we again apply this multi-parameter optimization procedure in the 2 steps, but for each step now we use the machine learning approach. And at the first step, it appeared that the quadratic regression model performs the best. So we performed the eigenfrequency analysis, but this is not pure eigenfrequency like we analyzed the eigenfrequency of the wind, but these are eigenfrequency of a wind which is surrounded by air. So we calculated 200 examples and generated another 1,800 examples. The R-score appeared to be satisfactory, and we used this model to analyze the sensitivity of our designs to different design parameters. But here is the question how to present the results, because as I said, we're in the 5-dimensional space, but we can read probably 2-dimensional graphs the best. So we decided to construct 2-dimensional maps similar to those used for our previous approach. But for that, we need to somehow get rid of the dependence on the other 3 parameters. And for that, we developed so-called reduced frequency functionals. So we took our functional obtained from the previous machine learning step, which depends on 5 parameters, and choose arbitrary 2 of them. So for example, in this case, thickness and scaling ratio, and calculated the minimum of this functional in terms of the other 3 parameters. This allowed us to construct a 2D maps for this 2 parameter function. And we did it for every pair of parameters. So we obtained many different of these 2D maps. Here are the examples of 2. And it appeared that they are quite useful. So how to understand them? So you see that, for example, in the figure on the left-hand side, we have the dependence on thickness and the scaling ratio along the x-axis. And we have a lot of blue, but also yellow region. How to interpret it? So if we are in the yellow region for these values of parameters, that means that our frequency, eigenfrequency of the wind, is at least 3 Hertz away from the excitation frequency. And because these data, they show the minimum of the reduced frequency functional, then they other parameters cannot be tuned to improve, let's say improve, to minimize the difference in frequencies. So that means that these values are not appropriate for our design if we want to deal with resonant type flight. On the other hand, another pair of parameters here shows completely different response, because the values in the legend, they're very small. That means that almost every choice of these values will give us very close values to the resonant frequency. Yes, because the difference, so here you see in colors, is of the order of 1/10. So this is how to interpret them. And then we used the similar approach, and again, quadratic regression model, to analyze the lift objective. And here we wanted to maximize the lift of the winds. So for that, we already performed, instead of eigenfrequency, we performed transient FSE analysis, for which we generated only 20 results, because it's very expensive to run such simulations. And then we calculated another 180 cases and fitted the model. Again, the R-score is appropriate. And we used that model to generate similar 2D maps for reduced lift, this time functionals, which give us insight about the importance of certain parameters as compared to the others, and also helps us to find configurations and the corresponding parameters values that satisfy the requirement of the maximum lift. So more maps and more details can be found in this paper, you can see here. Okay, and we end up with some conclusions. So in this 45 minutes, I gave you one of the first applications of mechanical metamaterials to design patterned artificial winds with controllable aerodynamic and aeroacoustic characteristics. Then we showed also that 3D printed polymers winds, which have metamaterial pattern, can be feasible solutions for resonant type flights. And this is something new that was not previously explored for airfoil-based winds due to their fragility. Then we developed the multi-parameter optimization scheme that allows to deliver multiple design patterns to achieve the target properties. And this is actually a step beyond optimization, because this approach gives the regions of the parameter values, indicates the sensitivity of the parameters, and at the end we can have not a single, but a number of designs with suitable flight characteristics. And this is something similar to what we have in nature. In nature, many insects have different patterns, but they are more or less optimized for their flight. So here we achieve a similar result. And at the end, let me put you in along the right direction. So I do not think that flapping artificial wings are solutions for everything. So that's why I do not expect to advertise that we will have soon aerospace structures with flapping wings looking like this. Although these structures exist and there is a separate research direction, so these devices are called ornithopters, and there are enthusiastic people developing flying devices with flexible artificial wings. Although it's still a long way to go to have a device that can carry a person probably, but still it seems to be quite promising research direction. And so at the end of this lecture, I would also like to advertise you to special issues, which I'm co-editing now. And the first one is especially close to my heart because it's initiative of the Frontiers publisher. They want to highlight the research of female researchers working in the field of acoustics and ultrasonics. And so if you are a female researcher and would like to have your work highly highlighted and advertised, please submit to this special issue, and we will treat you fairly and do all the advertisement work for you. And the other special issue is linked to the workshop that we had this last spring, but actually it's not limited to the participants in the workshop. So if you have nice results in the field of acoustic and mechanical metamaterials, please, you're very welcome to submit them to this collection up to the end of this year. So that's it from my side. Thank you very much for your attention.
Okay, thanks. Anastasia, thanks for your nice and excellent presentation. Actually, this is a very how to say, important application for the mechanical metamaterials. Okay, now it's the question and answer part. Maybe first, so Professor Wang will have some questions.
Okay, sure.
Yeah, thank you for your excellent lecture. I have one question. I found that the pattern of the wing you designed is periodic, but actually, for example, the wing of dragonfly, the pattern is not periodic. It changes gradually. So, is it possible to design a varying pattern of the wing?
Okay, thank you very much for this is an excellent question, and I got it several times because it means that people really want to imitate nature. So that's great. And by answering it, I would like to mention 2 points. So first of all, the non-periodicity of natural pattern refers to the fact that natural insects, they grow. Yeah, and during the growth, the grow process influences the patterning and makes it non-periodic. Second, in this study, we did not want to do any biomimetic analysis or it was simple bio-inspiration in terms of modeling the external shape of the wing. But we wanted to minimize the number of parameters, so only 5 in this periodic case, as you can see, to understand, can we obtain several optimized patterns or not? And now we know, yes, we can. And since the procedure works, we, of course, can now go to explore more complex patterns. It's just a question of computational time, because the analysis of the structures is really very complex in terms of computational effort.
Yeah, that's right. I think, of course, if we, for example, if we introduce a gradient pattern, I think the problem will be much more complex. I know, yes. But I think maybe the property of the wing can be improved, I think.
Yes, maybe not directly improved, but maybe improved too. But it definitely will be controllable property, because then we control the pattern, we can control the flight conditions and aerodynamic conditions too.
Okay, thank you. Yeah, thank you.
Thank you.
Okay. So other questions?
Yes, can you hear me?
Oh, yeah.
Yes, thank you for your impressive lecture, and I have a small question about the material constitutive. We know that the 3D printed polymer has some orientation when it is printed. I don't know whether should we consider this effect when we are doing some numerical simulation or something others.
Okay, another good question. Indeed, we also thought about this effect, and I tried to show you. I do not know whether you can see it on your screen or not, but these wings were on purpose printed differently. So some of them were printed with the pattern on top, the other on the pattern printed downside. So, and this resulted, okay, it's not very clearly seen, the sample 3, there are some defects in the pattern because it was printed on the opposite side. However, we noticed by looking at this very nice agreement in terms of frequency for different samples, that the small defects, they do not influence at least dynamic characteristics. What I think they will influence the noise generated because some defects on the surface of the wind, they introduce additional friction with air. And but for that, we need to implement experimental studies for real flap in flight. And this is something that we have not done yet.
Yeah, thank you. Thank you.
Okay.
Thank you.
Okay, so other questions?
I have a question.
Okay.
Okay. Hello, Dr. Kuzinski. I'm Wang, also a member of Professor Wang's group in Tianjin University. And thank you again for your excellent lecture. My question is, during your FIS, like the fluid structure interaction, so how to consider the turbulent flow? Because you mentioned about the laminar flow and low Reynolds number flow. So how to consider turbulent flow, because it is very common during the wind flying. So how to consider?
Okay, I'm not sure that I understood the question properly, but I tried to answer it, and then you can comment. So the choice of the laminar or turbulent flow, it is governed by the flapping frequency. If the flapping frequency is very high, then some vorticity in the air around the wind can be observed. And then, of course, we should consider also maybe compressibility of air. However, for the frequencies that we considered, and this is 25 hertz, so pretty low frequency, but at the same time, this frequency is common for many natural flyers, so that's why we do not do non-realistic study. It was shown that the effects of the compressibility of air and of created turbulence in air, they're very small and they can be safely neglected. So that's why we assumed laminar flow. And because we also do not consider forward motion of wind, then this assumption is quite valid to obtain realistic results.
So thank you. And I have another question. So what's the numerical simulation do you use during your numerical simulation? So have you used the larger ID simulation or direct number simulation?
Yes, we consider a fluid structure interaction problem, and within that, in COMSOL, and there we have a separate part specifying the dynamics of air. Yeah, this is our fluid. Then separate package, let's say, simulating the motion of the wing, which, as I said, experience large deformation. So this is this equation that describes it. We do not neglect large deformations that are there. And then we couple these two domains by introducing some already available Lagrangian Eulerian approach in COMSOL. So we do not modify standard settings that are there.
Okay,
Yeah.
okay, thank you so much. Thank you. Okay.
Okay, so other questions?
Not yet.
Not yet. Okay. Okay. So actually, I just have one small question. Actually, it's also similar to the question asked by Yu Xinfu. The second question is also about the material parameters. Because actually we have read your paper you just mentioned in the advanced functional materials, which is about the dispersive of phonic metamaterials. And we know that generally, if we fabricate the samples by using 3D printing or other software or other how to say methods, and we should do some simulation to compare the results of the simulation and the experiment. But the question is how to determine the how to say the material parameters used in simulation. Actually, this is I think this question is being asked frequently, maybe also for you and also for me actually. But generally, I'm just wondering how you are considered about this, especially because at first, as he said, generally for 3D printing, the material should be anisotropic. It's not at least it's orthogonoisotropic. So, but generally we will consider it as isotropic to simplify the the questions.
Okay.
So
yes.
What's your thoughts or opinion on this?
Okay. Yeah. Very good and very comprehensive question. So I can give another lecture on this topic.
Okay.
But I try to answer it in short.
Okay.
So in the advanced functional materials paper, we did not consider 3D printed materials. Yeah? So we considered materials which are produced by standard techniques. And this for epoxy, which is produced by molding process here. And we considered let me remember, polycarbonate or PMMA. Yeah, PMMA. So for these materials, we do not have very pronounced orientation, so they indeed behave isotropically, not anisotropically, because for 3D printed materials, it's, as you said, it's an isotropic response and also non-uniform density, it's additional porosity, so it's very complex material to analyze. But for conventionally produced materials, the viscosity is caused by the connections and interactions between the polymer molecules. So if we want to really measure their properties, we must understand what's going on in the material and apply the techniques which are appropriate for studying this behavior of polymers. And most common technique is so-called DTPA analysis. This is dynamic temperature method or analysis. There, it is applied in two settings, and but it's limited. So the applicability of this analysis is limited to linear elastic materials. So if we know from some other sources that the material can behave non-linearly, and in that study this was epoxy, then that technique cannot be applied. But as a first step, we can still make a try. Yeah? So this technique implies that we take a piece of material and excite it dynamically for example, as a first step, at different temperatures. We excite dynamically on commercial machines in a limited frequency range. Typically, this is from several hertz to maybe 100 hertz or 200 hertz. But we can do it at different temperatures. So we start from low temperature, and then we increase gradually the temperature and excite in the same frequency range and record all this data. And then we say, if material behaves linearly, then we can apply so-called dynamic temperature superposition principle. Then these measurements, so this principle means that the changes introduced in the material viscosity by temperature are the same as those introduced dynamically. And under this assumption, we can shift the measured curves to a larger frequency range to obtain so-called master curve. And this curve will provide you the dependence of the elastic moduli on frequency. And the type of elastic moduli you will have depends on the type of your sample excitation. So if you are interested in shear modulus, you can apply dynamic shear excitation at different temperatures. Torsional excitation, sorry, then it will give you shear modulus. If you are interested in Young's modulus, you apply dynamic excitation, like extensional excitation at different frequencies and different temperatures. And in this way, you construct the master curve, which is the dependence of the moduli on the frequency, and then you can use it in generalized Maxwell model and yeah, basically model the behavior of phononic structures made of this material. If you have 3D printed material, then, so first it's not clear, and at first it should be established whether the material behaves linearly in terms of viscoelastic properties or not. If it is like that, then the same test should be repeated, but then taken into account the orientation, yeah, of the sample, of the printed sample. And then you obtain directional moduli in different directions. However, if the material is not linear, the dynamic temperature superposition principle does not apply, because the changes induced in the material by changing temperature are not the same as those induced by frequency. And then you need to reconstruct the curve of the dependencies at the frequency range that you're interested in by applying the specific technique, but not this principle. Does it clarify a little bit?
Yes, actually, it's how to say? I understand it more clear, but yeah, and still, maybe it's a question that to be answered in the future, because
yeah,
I think so generally the simulation and the experiment that they cannot how to say match exactly. I mean, so it means still we have some space to improve. Maybe not only the material parameters, but also other things like the boundary condition and computations. Yeah. Okay.
Because in modeling phononic structures, we really have very complex problems. We not only have material viscosity, but we also have variations in the amount of material, right? So we can have, for example, is in that example which I showed, just a second. I cannot go out of full screen regime, but it will not take too much time. Like in these structures, then we have variations between bulky parts and slender parts. This is also very difficult to capture when we consider viscoelastic moduli. Yeah, and for 3D printed materials, you also need to have in mind that the behavior of the material inside the printed structure is very different from that on the surface. Due to the printing conditions. Yeah.
Okay. Thanks for your answers and explanations. Okay, so my last call, is there any other questions? 大家还有没有其他问题? Okay, so if no, it's already, yeah, the time is
yeah.
ready. So finally, I would like to say thanks for your excellent presentation and also for your excellent answers for this question. And we do hope that, as I said before, so next year I hope that how to say, the border is free, so that we can invite you to visit China and visit Tianjin. And I hope that yeah, in the future we can meet face to face, not only to discuss online, but also discuss face to face, and have some
sure.
potential cooperations in the future. Yeah.
Okay, thank you very much one more time for the invitation, and I wish indeed that China will a little bit soften the regulations around the COVID, because I see my students also struggling. They cannot visit their home for 2 years. So it's quite frustrating for them too. And indeed, maybe in future it will go better.
Yeah. Things are getting better, I think. Okay.
Great.
Okay, thank you. Yeah.
Thank you.
Yeah.
Bye.
Bye. 王老师，你那话筒没开，你到这后边来。
Okay, thank you for your lecture.
Okay.
And welcome you to China someday. Bye bye.
Bye bye.